So linear talk number 16. So orthogonal vector, orthogonal basis, and Gram-Schmidt orthogonalization. So these are very important topic in linear algebra and especially in non-linear space. So we see in the last class that the idea of angle in inner product there is the idea of angle. So if there are two vector, if V is a non-linear space, so it is a vector space with with a norm with inner product, then norm actually gives the distance and inner product gives the angle. So if there are two vector x and y, such that x and inner product of xy is this, then we is non-zero. Say if it is 0, then the angle between x and y is undefined, so it is not null vector. Then this norm of a norm can be formed by this inner product, just inner product. So this is root over inner product xx. So this is cos inverse of this is defined to be the angle, and by Cauchy-Schwarz inequality we can prove that this is just lies between -1 and none. So there's a cos inverse is defined. So this is the angle of between two vector in general sense. Again, it is general sense means it is not only in Rn. In R3 it is just angle. We have the idea of geometrical angle, but in Rn there is no geometry. But it's not only in the Rn, basically in the abstract set. This is the angle between two functions also. So if there is a function space, is a nonlinear space, something like a set of all smooth function or continuously differentiable function, then we can talk about the angle between sine and cos. That also here include if there is some inner product is defined. So this angle is a theta. So is not only for 2D, not only for R3, not only for Rn also, this for any general abstract sense, abstract vector space. So when this angle, two angles are say perpendicular, so we know this something two vectors are perpendicular if the angle is 90 degree, and if it is 90 degree, that means this is 0, if and only if this inner product is 0. So because this remember that since x and y is not 0, so norm x and norm y is not 0, so it's positive. So if inner product xy is 0, this is if and only if, then this cos inverse this thing is so that angle theta is 90 degree. So and it is obvious in R2 or R3 or in general Rn, because in R3 we take inner product as a dot product. There is obviously a question: is there any other inner product in R3? Can we define any other inner product other than dot product? That is a good question. Whether this inner product is the dot product is the only inner product in R3 or not. But this dot product is inner product, and dot product, this is 0 means it is 90 degree. This you can prove in R3 just geometrically. No need of this vector space or this thing. You can just by Euclidean geometry you can prove it. So these are, if the x and y are two vectors such that this inner product xy is 0, then it is called orthogonal vector. So orthogonal to each other. So x and y orthogonal to each other. Now if there is a set, say x1 x2 is a collection of some finite or maybe infinite set, then it is called orthogonal set if xi is, by the way, if this is 0, we write x perpendicular to y is orthogonal to y. Sometimes it's called x is orthogonal to y or x perpendicular to y. So just this perpendicular to xj for all I not equal to j. So that means your x comma xi comma xi xj inner product is just equal to inner product that delta ij, this Kronecker delta, and norm of xi and norm of xj. So if I equal to j, then it is just xi xi, so which is xi norm of xi square. and if delta ij not equal to j, I not equal to j, then delta ij is 0. So it is 0. So it's conical delta. So this is the orthogonal set of vectors. Now there is one more concept. You say that, say this is the S. Now if there is some collection of sets, S1, S2, Sk, and each have some vectors. So S1 is subset of V, S2 is subset of V, Sk is subset of V, vector space. So S1 have say 3 vectors, S2 have say 5 vectors. This collection of set is called orthogonal to each other. So if we call say S1 is orthogonal to S2, that means each vector of S1 is orthogonal to S2. So this whole collection is orthogonal to S2 means means this for all x belongs to S1 or x1 belongs to S1 and all x2 belongs to S2 is x1 is perpendicular to x2. So in between the S1 the vectors may not be perpendicular, but from a vector from S1 is perpendicular to vector from S2. Sometimes we write x is perpendicular to S. That means each vector of S is perpendicular to x, or x is perpendicular to each vector is just symmetric. If x is perpendicular to y, then y is perpendicular to x. Now, if say S is a collection of vectors, and you can easily generate the span that span of S is again is a perpendicular to x. So any vector from the span of S. So if x is perpendicular to S, and if you take any linear combination from S, vector from the S, then that also perpendicular to x. Finite combination. Linear combination is always must be finite. The span means if it is a set of this set is uncountable count infinitely many vectors, still this span is always this finite linear combination. So if it is finite linear combination by distributing property and distributive property, you can easily prove that if x is perpendicular to y1, y2, yn, then x is perpendicular to that linear combination of y1, y2, yn. So collection of set then that means is if I have a vector, it's a non-null vector or maybe a null vector, and this all the vectors which is perpendicular to that vector is forms a subspace basically of V. That is interesting. Now there is a very important theorem. It's called Pythagoras theorem. If x and y is perpendicular, then the very interesting thing is x plus y whole square is just x square plus norm of x plus y, norm of x plus y whole square is just norm of x square plus norm of y square. This is very, very interesting. So it is just Pythagoras theorem in general inner product space. So it's very amazing or it's interesting to see that whether it's just a Pythagoras theorem is Pythagoras prove it for two-dimensional case. But interestingly, it is true for not only in R3 and not only in Rn, it is eventually true for any general version, any general inner product space. If you introduce a inner product, then this is a very interesting result by Pythagoras is still it is hold for any arbitrary inner product space. The proof is just trivial. Just proof is very trivial, just a one-line proof. This is basically by definition this norm of x plus inner product x plus y inner product x plus y and x plus y. Now using distributive property, you can easily show this is just x y and yx. You should write yx because yx may not be xy if it is not in R. If it is R on R, then it is yx equal to xy. But if it is inner product defined on C, then yx is just xy conjugate. Inner product yx is the inner product xy conjugate. Then yy. Now this goes to 0. This is 0. So since they are perpendicular, these both are 0. So whatever this is, yx is xy inner product or conjugate, this is 0. And this is by definition, this is inner product norm of x square plus norm of y square. So interesting, very interesting case. You can just Pythagoras theorem you can prove just in one line using this inner product sense. So it is not only true for R3 or Rn, it is actually true for in general case. So this is very important and very just fast theorem and very useful and most popular theorem in geometry. We just generalize this version, generalized version of this Pythagoras theorem in general inner product space. This is very interesting. So this concept actually came from this orthogonality, and this is actually by the inner product. If there is no inner product, then we can't say about this. Maybe there is a norm. Maybe there is a norm, but inner product is not there. Then we can't talk about this thing. Maybe there is a norm. So norm is defined. Say, so norm of x plus y whole square is defined. Norm of x square is defined. Norm of y square is defined. But we don't know that maybe equal or may not be equal, whatever. Because if there is no inner product, we can't prove like that. Maybe they are equal, may not be they are equal. So this depends on the norm. That norm, what we define. But if it is inner product, that norm is coming from the inner product, then it is true. True, the Pythagoras theorem is true. So this is a very important thing. And next, orthogonality and independency. This is very important. So if there is a orthogonal is a set which is each are orthogonal to each other, and every vector is orthogonal to each other. Is there independent? Yes, they are independent, except one case if there is no zero vector, because zero vector is always orthogonal to any vector. So 0 is orthogonal to any vector. If there is no such no 0 is there, so xi is not equal to 0 vector, null vector, then this is the set. This, if it is an orthogonal set, then this implies this is an independent set. But the converse is not true. This independent is not the orthogonal. It is trivial, because if you take in say R2, if you take just 1, 0 and 1, 1, they are not orthogonal. But these two vectors are independent, but they are not orthogonal. But if it's once it is orthogonal, then this must be independent. And you can just easily prove this is by just taking C1 x1, C2 x2, dot C and xn, say equal to 0 vector. Now you just take the inner product with this, any xi. Now by distributive property, you can easily show that we just inner product take with the right side better. Otherwise, you have to take the conjugate part. So better from the right side. So this implies actually C1 x1 xi and dot. Now this everyone is killed except the only one thing, which is xi, because all are orthonormal. Xi is orthonormal to each other. Xi is orthonormal to other xj's where j not equal to I. So only this, all these are killed, and only this Cj, Ci norm xi square is there, which is 0. But norm xi square is not 0; it's positive because xi is not 0. So Ci is 0. So interesting, Ci is 0. Right? You can do it any I. So orthogonal set of vectors is independent. So that is very interesting. And then orthogonal, if they are orthogonal, if the two sets are orthogonal, if say S1 and S2 are two different set, or the two set different subspace actually. If S1 is orthogonal to S2, then the span of S1 is again orthogonal to S2. So that any vector from S1 is orthogonal to the any vector of S2. So fix a vector in S2, take a linear combination of vectors from S1, that must be orthogonal to that fixed vector of S2. And similarly, if you take a fix from S1, and if you take any linear combination of S2, that must be perpendicular to the fixed vector in S1. So that means if you take all linear combinations, linear combination is always finite linear combination from on S1, that actually perpendicular to S2. So you have a S1 and S2 to perpendicular orthogonal set. That means each vector of S1 is perpendicular to each vector of S2. Now the span of S1 is perpendicular to S2. Then next you will see that span of S2 is perpendicular to span of S1. So it is like called bootstrap principle. You say first S1 and S2 is orthogonal, then you show the span of S1 is orthogonal to S2, then you show the span of S2 is orthogonal to the span of S1. So this is something called bootstrapping. And this principle, basically, this principle is called the bootstrapping principle, one by one, just one after another. Just not showing that just to take a element from span of S1 and take an element from span of S2. Don't do this. So one by step by step. So this is, or so orthogonal, then this is maybe we just consider subspace. This S1 S2, and if this S1 S2 subspace and they are orthogonal, then this sum is actually direct. This sum is actually direct. This sum is direct. Basically, this sum is direct. This is trivial to see that why this sum is direct. So, because the 0 is the only element common to both of them. Because if 0 is not any other 0 other than 0, there is a common element. Say y is common in the space S1 and S2 both. That means y is not orthogonal to y. No, it is not equal to 0. So y inner product y is not 0. So is not y is not orthogonal to y. So there is element in S1, there is element in S2 which is not orthogonal to each other. So contradiction. So 0 is the only element common. So this is very important. These two things are very important. Once there is a orthogonal set, that must be independent, and if there are two orthogonal set, then their sum is direct. Direct means there is some sort of independence in the two different set. You see, there's two concepts: the independence in a single set, and there's independence between two different sets. Obviously, the S1, the element of S1 may not be independent. S1 element of S2 may not be independent. Vectors of S2 may not be independent. So the elements of the vectors of subspace is not independent. Next, just one step advanced concept is just orthonormal. So what is orthonormal? It is just orthogonal, and the norm is 1. So it's just like a vector is a unit vector. So this set is called orthonormal set, like orthogonal. It's just all this norm is 1, and this for all I and j. This is true for all I and j. I not equal to j. So, and this is for all I. So this is orthonormal. It's like a unit vector. What is the advantage? Then xi xj is just delta ij, Kronecker delta ij. So it is called orthonormal set of vectors. Now again, there is a same concept is if the two set are there, if they're both are say unit vector. No, you can't actually generalize this concept of orthogonality between two vectors, because the orthogonality between two vectors, and this norm is 1 is a single for a single vector. So if there is a set S1 and there is a set S2, you just say that every element of S1 is unit, that you can say, and every element of S2 is unit, that you can say, and you can say the element of S1 is orthogonal to S2, element of S2, that you can say. But this is not a generalization of the orthonormal case. So orthonormal thing you just generalized for a single set. So there is a set which is orthogonal. You can just extend to orthonormal, means you just take the unit vector for every vector, that xi divided by norm of xi, because this orthonormal orthogonal set is not containing the 0. If it is contains 0, then it is a problem. So it's not independent. Now these are independent. We know this is orthogonal or whatever is orthonormal. Orthonormal is again orthogonal. This is independent. Now this maybe forms the basis. If so, this is a basis. If this is say there is a basis which every elements are unit and this is orthogonal to each other, then it is called orthonormal basis. So very important thing is called orthonormal basis. Is a very important part. So it is a set of orthonormal, orthogonal, and unit vector, and it span the whole vector space. So once it is orthogonal, it is independent. So it's just a spanning is needed. So there is a set of unit vectors, collection of unit vectors, such that each are orthogonal to each other, and it span the whole vector space. Then is the orthonormal basis. Now the question is, there any always there is orthonormal basis exist or not? Now for a finite dimensional vector space, we can easily show that by Gram-Schmidt's orthogonalization process, this is exists for every finite dimensional vector space. Not only that, we just actually show much more than that. We will show if you have a orthogonal set of vectors Or if you have an orthonormal set of vectors, you can just extend that set. Because say if you have a collection of vectors, an independent set of vectors, you can just extend that set to the basis. Otherwise, there is a problem is easy. If you have a, say, I give you a collection of independent vectors and I ask you give a basis, you can just give any basis. Just give me the standard basis. So you have, you know what, there is a basis. So if someone asks you that this is my set and you give me a basis, you can just give a fixed basis. So this is not an interesting thing. Interesting thing is I give a set of independent vectors. Obviously, the set must be independent, otherwise it can't extend to a basis. So I give you a independent set of independent vectors, fine dimensional vectors, let's say, and then you just extend that, and we know how to extend this. The very first lecture 2 or 3, we show how this extend. This you just span this and then take the one vectors from the outside, then include that, and then is a bigger spanning, then one by one, and you reach that basis. So same thing, you start with an orthogonal, say maybe say orthonormal first. If it is orthonormal, you can easily find the orthogonal. So if it is orthogonal set, so obviously it is independent. Now can we extend this? Now we can always extend it to a basis because we know this is an independent set, so we can extend to a basis. But the extra condition is you have to extend to orthogonal basis. Orthonormality is always we can do in last step. So question is that if there is an orthogonal set of vectors, can we extend this to an orthogonal basis, or there is orthonormal set of vectors, can we extend to orthonormal basis? If I say yes, we can do this, then with that question whether there is existence of orthonormal basis, there is orthonormal basis or not, the answer is yes, because we start with a single element, just with a single element other than 0, and this is orthonormal set. A single element other than 0 is orthonormal set, orthogonal set, or just take a unit vector which is orthonormal set. I just extend. And this extension procedure is just Gram-Schmidt orthogonalization process. This is very interesting, and it's a very intuitive and very interesting geometry. So we just consider for a 2-dimensional case. So I have say one vector, this vector set. Now I want to extend this, or maybe there's one more question we can ask, that okay, I have a basis that may not be orthogonal or orthonormal. Can we find a orthonormal basis from this? So why this question is related to that? Because like that. So we have a also orthonormal basis, orthonormal set of vectors or orthogonal set of vectors, whatever. Now first we extend this to the basis, and then in some procedure we kept this the initial set as it is, and now we change that the extra basis what is extended such a way that the other basis, the excess part which you include later, is orthogonal to the previous thing. That is the idea. So it is just one by one. So this is one vector. So how do you take another vector is orthonormal to this? That is very easy. You just take the perpendicular vector. But the question is, if I have another vector which is given to me, say this is the vector given to me, and can we form a orthogonal? If you have orthogonal, orthonormality is easy. Set of vectors such that this is from these two set of vector. At least so red should be there. So you just red is there. Just change blue so that this blue to the green vector, so that green and red will be a orthonormal vector, and since there are two vectors in the 2-dimensional space, it is all basis. So idea is clear. So you want a vector which is perpendicular to the red one. So that means we drop a perpendicular from this to this, and so once we have the perpendicular, so this is actually the component of these two. So this green is actually the sum of this red portion and then the green portion. Now if we just take the difference of this blue minus this portion of red, that will give you the green thing. So this story code. So and that give you a orthogonal vector to the red. So idea is clear. So if I have a vector, say this red vector is say x, and this blue vector is y. So green vector is z. So we want to find z such that it is just y minus something. Now what is this something? Y is the green, that blue vector, and x is the red vector. So what is that something? That is called the projection. That is called the component. Sorry, it is not a projection. Projection is the length of this vector is called projection, and this whole vector is called the component. So it is a component of the blue vector, the y vector, along x vector. Now in our previous in school geometry or school vector this is in vector thing or in physics, we know how to find this. This is nothing but the dot product of x and y. So just the dot product means here it is inner product between x and y, and then must be divided by the norm of x. That part is actually the component, and we need this is the component part. So this is the length of this. So we need a unit vector along this. So we need a unit vector along this. So unit vector along x is x by norm of x, and this the length of this part is, we know this is say x dot y is just x norm of x y cos theta. So we need that y cos theta only, not x y cos theta. We need that the part, that projection, that part of the red is marked by the green, marked as green. That is just y cos theta. So that means it is x dot y divided by x. That means x inner product y divided by norm of x. And this is the length. So we need this vector component. This is a projection. This inner product y divided by the x norm of x is the projection of x along y. Projection of y along x. And the component of y along x does the vector thing. So it is that scalar multiplied with this unit vector along this direction of x, which is x by norm x. And this is nothing but you just write in terms of inner product. This is just y minus xy inner product, and then divided by x inner product, and this x vector. Precisely z is this vector, and you just want to show that z and x is just dot product is 0, and we can easily show that why it is dot product is 0. It is trivial to check why this dot product is 0. Why this inner product is 0. It's just xy, then x's cancel out. By the way, this x and y are both non-zero vectors. So x inner product is cancel out. So xy just 0. Now, what will be the next step? Is that in R3? What will be the next idea? Or the Rm is already, we extend this to the say up to the kth dimension. We have already this x1, x2, xk, which is orthonormal. It's not basis. We have a new vector, say y. How do you find a vector z such that which is orthogonal to x1, x2, xn, and then you can find the orthonormal. So once you find z, you just take the divide by the norm of z. That will be the unit vector. And if you do the two different way, you just first the orthogonal set of vectors, which is basis, then you just normalize this. Or you can every step you just normalize. If you every step you normalize this then it will be better in the sense. Then this norm of this inner product xx will be 1. There is no denominator. Denominator will be 1. This part. So whatever, you can just do it in every step, or you can in the last step. Now the idea is again same. So you have a already you have a space spanned by this x1, x2, xk, and you have a blue vector which is y vector, and obviously you need the projection again to this subspace, to this subspace. To this projection, this to the subspace, and this red portion is the component, and this green portion is actually, red portion is the component, and this green portion is the z actually. Now this is your y, this is your y, and this is your z actually, and we need to find the projection of y along this subspace, this red part. Red part, if the red part is w, this is actually y minus w. So it is how to find the w. So w again is clear that w will be that dot product between every xi with that y, and then divided by this. If it is a 1, then it's just 1 is norm. Then sum over all this I equal to 1 to k and this xi. So it is just, this projection is nothing but, this component on the subspace is nothing but is a sum of the component to the every each basis vector. And this beauties came from the orthogonality, which is not orthogonality actually. If it is an orthogonal thing, then this will not have so you just find the component to the each basis vector and this just add, you will find the component on the whole subspace. And this is not true for in general. If it's not an this is an orthonormal, the x1 x2, if the x1 x2 is not orthogonal, then it is not true. Now the proof is easy, just easy. We just x that y, you just take this vector and you just put this with this xi or xj. Now everything will be killed, only xj will be there. So j in the sum, the I, when I equal to j, then that will be there, and otherwise everything will be 0. So just in denominator is xj, numerator also is xj, here it is xj and this is xj. So everything, so it is 0 for all j. So this vector is actually orthogonal to each other. It's very easy, trivial by this geometry, and this is very important. And you know, this is very popular process or method in linear algebra. This is called Gram-Schmidt orthogonalisation, but this is very trivial, just very easily you can just visualize this thing. It is very clear or natural intuition using just this projection of this thing. So it's actually a projection of a vector along another subspace, which that vector is not in there already. So this is the basic idea, and this idea actually leads to another concept which is called the best approximation thing. Same thing. See, this idea have a best approximation. So if you have a subspace here, maybe it is not the R2, maybe it's R10, or maybe in general abstract non-linear inner product space, and then this red is not in the subspace. So if this red is not in the subspace, what is the best approximation? What is the best vector you can take from this in this subspace, this black subspace, which is closest to that red vector? And obviously this is nothing but this projection of this red vector along this subspace, and along this subspace, if you have an orthogonal basis to, or orthogonal basis, you have an orthogonal basis of that subspace, then this finding the blue part is very, very easy, because the blue part is nothing but the sum of the individual component of the red. along the every basis vector, and they just take the sum. Because this, if we once this basis is orthogonal, orthonormal, then the finding the corresponding component. So again, if y may be in the subspace, that if red vector is a subspace, so y may be written, can be written as c1 x1 plus c2 x2 cn xn, and this finding c1, this ci's are very easy here. Just ci is nothing but just inner product y and xi. If it is an orthonormal, x1 x2 xn, and if this is not in that subspace, then you can't write that yi as a c1 c2 cn, but we want to find a c1 c2 cn as a c1 x1 plus c2 xn cn xn, that is the closest to y. In which sense? This sense is this: if the norm of between this y and this c1 x1 plus c2 x1 x2 xn orthonormal basis to this subspace, that should be the minimum over all ci. So choose such a ci that is minimum. This distance is minimum, and this distance is clear. It is minimum if you take the projection. This is the component part, and the distance is actually this green portion, and this you can easily find from the Pythagoras theorem. What will be the distance? The Pythagoras will help you. What is the actual distance between this, the minimum distance, and you can easily find what will be c1 c2 cn. This is nothing but the c1 c2 cn's or ci's are just the yi xi. Just yi xi. Remember this xi in the right side. Otherwise, there is a conjugate thing in complex field. So it's just ci, and if y is in the subspace, then this distance will be 0, and this ci will give such a vector which is give 0, because in that case that vector is itself y. And in not only that by Pythagoras theorem, the interesting thing is this vector is unique. This minimum vector is unique. The minimum distance vector is unique. You can easily prove by Pythagoras theorem. Pythagoras theorem shows that actually this projection, that part, that distance, this distant part, this is unique. And this is why orthogonal basis is useful to the find best approximation. So this is all for this orthonormal and this best approximation theory using orthonormal basis.